So for the series at World StatPeace 2025, we today have Lorenzo Caprini from the Humboldt Marie Curie Fellowship in Germany at Düsseldorf. So Lorenzo, can you please introduce yourself? Tell us what are your interests, what did you study?
Thanks for the introduction. I mean, currently I am employed at the University of Rome as a tenure track researcher, basically junior professor. And but before I was in Düsseldorf through the Marie Curie and before Humboldt fellowships. I started with a PhD at Gran Sasso Science Institute in L'Aquila, and starting from that period, my research about active matter system started, and then continued towards more collective phenomena later. Say, active matter. So what does it mean? It means that it considers systems that are typically out of equilibrium and that can be considered as living systems. Typical examples could be bacteria, sperm, but also other microorganisms, more complex microorganisms such as cells or even tissues. So the tissues of our body, the living tissues, these are typically these are typical active materials. And what does it mean being active in general? Why all these systems are active? The reason is kind of simple. They distinguish from ordinary materials, so the usual liquids, solids, or gas that we study in the textbook and that we learn in the university classes or even high school classes. They differ because the system usually take energy from the environment and then convert such an energy in order to perform motion or even more complex tasks, more complex functionalities. And this means that these systems are able to kind of self-organize somehow, exploit collective dynamics, self-organization dynamics that allow them to perform really complex tasks. So imagine, for instance, birds that you can see in the sky. This system here, through a sort of alignment interaction due to visual perception, for instance, they align themselves and form this complex pattern that you can observe in the sky that are also used in biology against predators. So against another predator that comes from the sky and want to attack and want to hunt one of these birds of the storm, and they move together. They collectively organize in order to defend. So for different purposes, for instance. But this happens also at the micro scale, like sperm in the so for instance, sperm in vitro or in the body in general, they move together, they orient and they follow a path promoting optimal navigation strategy in order to perform the task, so to reach the ovulus, basically. And these are just a few examples of this complex world of active particles, of active matter that is around everywhere. It's everywhere around us. So yeah.
Now, the interesting point of active matter is essentially that it can create patterns that are not, say, observed in equilibrium or in inanimate systems, no? Because in general, you assume that the system evolves towards increasing entropy or minimizing free energy and so on. But active matter does something completely different.
Yes, active matter does something completely different. Indeed, in active system, we are permanently out of equilibrium. There is this transfer of energy from the environment to the system to perform work that is continuous in time. It means that also for long times in the steady state, this system continuously produces entropy. And somehow these are out of equilibrium. That means that there is no an equilibrium-free energy, at least in the models that are usually considered to describe such a system. And this is the standard situation of biology, so biological microswimmers, but also more complex systems such as so robots at the macro scale that are still active, or this kind of active granular particles, or more in general animals. These are what usually happens, and this poses big challenges also from the theoretical side, because there is not a theory that somehow is able to understand the physics of this system from a fundamental level. And for this reason, there is also a big theoretical activity that aims to develop a framework, a theoretical framework, to understand some basic principles, something that link all these systems together and is able somehow to predict, to explain these collective phenomena. And the reason is simple. If a theory would exist, then it would be even possible to predict this collective motion, this collective arrangement, and this would have really promising application for the future, for instance, for building novel materials. So materials that are kind of able to form a structure that can self-repair, for instance. And this is because of the tendency of active matter to cluster spontaneously at wish, let's say, or due to an external stimulus. And then also to make so for instance, another application that was proposed also in La Sapienza a few years ago is an engine that is powered by bacteria. This is because active matter systems are typically able to persistently push the boundary. They are not controlled by the Maxwell-Boltzmann distribution, so they are kind of able to spontaneously break asymmetry, and this symmetry breaking due to the persistent pushing effect of bacteria, colloids, or active colloids, or whatever active system is able to promote a rotation of an asymmetric wheel, contrary to equilibrium system, where this kind of effect is impossible. So this is just to say that these active materials poses challenges for what concern novel application, new technology, innovation that could also impact the everyday life experience, perhaps in the future.
I've read that you not only develop theoretical models, but you also participate in experiments. Can you describe some of them?
Yes, at first I was involved in collaboration with experimentalists, for instance, in a project that was funded by Lazio, by the region Lazio, about sperm in confinement. This is a project that was carried on with Andrea Puglisi and Roberto Di Leonardo in La Sapienza and CNR of Rome. And for this kind of collaboration, I was used to perform numerical simulations. And the same, I did the same in more recent experimental work about active colloids in complex environment, let's say. So for instance, in crowded environment due to other particles or due to motility landscapes. And but I want also to mention my recent experimental activity. From my permanence in Düsseldorf in 2021, I started building 3D printed robots. So these are kind of small objects, like with a cylindrical body and some legs attached, that when put on a plate, start moving. And the reason is that they have an internal motor that pump energy into the system and allow the particle to run, to walk around this space, and somehow mimic the behavior of this biological active system. So mimic the behavior of bacteria, but of course at the macroscopic level, so we can see with our eyes what's going on. And so putting many of them together, we were able to study collective effect, collective phenomena. This system cluster spontaneously, so they like to stay together, and sometimes they also develop the tendency of moving collectively, showing groups that move together, and these are as of course kind of strong potential applications in many fields. So for instance, these 3D printed robots were taught to explore complex environment that cannot be. So for instance, deep in the ocean, it's kind of unlikely that a human person can go to visit. But we need somehow something at some technologies that are able to explore these spaces. Or just to make another example, is exploration on other planets or rescue mission could be kind of powered by the use of this material that are efficiently explore the space with some randomness and are somehow able to look around to explore everything. And of course, behind this, there is also a possibility for the future that is the one of linking this potential technology with machine learning in such a way that this kind of vibrobots are able to learn themselves where to move, are able to increase the efficiency of their motion to perform this task kind of in a more efficient way through machine learning approaches, let's say. And this is say a future direction of research.
An interesting question is what is the essential ingredients to make a particle active? I mean, birds have a brain, so you can imagine that they perform some actions because they elaborate information. Bacteria probably do not have a brain. Surely they do not have brain, but they can still elaborate information. So I wonder, but maybe a molecule not. A molecule behaves in the standard way. So I wonder which is the threshold of, say, individual information elaboration in order to have these collective phenomena.
Well, the ingredients behind collective phenomena are typically simpler than what you can expect. They are just ruled by this transfer of energy. And this transfer of energy leads the particle to move in a non-thermal way, like as if they are driven by an internal degree of freedom that power the motion in one direction, that somehow breaks an internal translational symmetry of the particle or a rotational one, and this breaking allows the particle to move. This motion here is the simpler possible case of activity of active matter system, and this is called self-propulsion. And of course, this kind of energy conversion can lead also to more complex behavior. Like, for instance, a cell that duplicates is still active. Is because, of course, this duplication effect is something that is irreversible. There is no way of allowing the two duplicated cells to move back and collapse. They can just continue their life, and they can die perhaps at some point. But so that's another point. So active matter is is a theoretical framework, is a class of system. Let's say that at first want to model living systems. So the life itself is kind of active, is activity, and then of course from this huge perspective, there are many directions that can be followed. So the simpler one is the motion, so self-propulsion, but then there are also many other way of manifesting activity. And so another one is a spontaneous body deformation, body oscillation. This is another typical feature of cells. They kind of the cells they breathe somehow, so they expand their bodies, and then they contract, let's say, and this is say another way of talking about activity.
So for finishing, you received the prize of the UPAP for young researchers in this year. But it was somehow unexpected. You mentioned it before this interview, or I mean, you are. So I think you are glad not to have received this prize.
Yes. Yes, I'm really glad indeed. I mean, I was really happy to be chosen as a early career. I mean, for this early career award, and yeah, I think it's. I mean, for me, it was a great honor, of course, and so I thanks people that support my. My application that I mean that apply for me and yes, I think it's I think it's a good opportunity that in StatFis, so there is also a small space dedicated to young researchers. This is that kind of the future of the field, and that somehow I mean needs to be needs support, let's say, and of course an award like this is a great honor, and it's yeah, it's something that is of course highly appreciated.
So finally, what are you bringing to StatFis? What will you hear from you here in Florence next July?
You mean as a talk?
Yeah.
I will talk about chiral active systems, so systems that are characterized by an internal rotational symmetry brigade that somehow, when they interact, they transfer also angular momentum. And this is at the basis of a new collective phenomenon that I call BIO, that means bubbles induced by odd or transverse interactions, and that spontaneously arise in a liquid, let's say a liquid of this particle, that through these simple rules spontaneously develop voids, periodic voids in the system. And this is again a collective phenomenon typical of I mean, that is new in active matter. So far there was the tendency of showing clustering, something called motility-induced phase separation, or it was show also the tendency of moving together, so with the so-called flocking. This is a new effort. This is a new phenomenon, and somehow offers an intriguing perspective for future studies in this in active matter. And it's general because several chiral dynamics are that now, I mean, that I'm exploring also now in this in this month specifically. These are all able to show this bubble formation, to show this biophase that I have recently discovered together with Umberto Marini and Bettolo Marconi, and also a master student that is now working on this, that is Alessandro Petrini.
Okay, so thank you, Lorenzo, and I'm eager to hear you here in Florence for the next July StatFis. Bye-bye.
Yes. Bye.